Alright, let's explore the fascinating world of hash tables. Imagine you have a special container where you want to keep things organized. These things comes in pairs, each with a unique number and some important data. Think of this unique number as a special key, like a secret code that only that thing knows. And the data that goes with it is like the treasure that's hidden and protected by that secret code. So, in our magical hash table, each item has a key that's like its ID card and a value that's like its hidden treasure. And the beauty of this is that when you want to find that treasure later, you don't need to search the whole container. You just tell the table the key and it quickly gives you the treasure associated with it. It's like having a special map that takes you straightly to your treasure chest. So, in simple terms, a hash table is like a super efficient organizer that pairs up unique IDs with valuable items, making it easy to find what you are looking for without any fuss. Key is unique integer that is used for indexing the values, and value is the data that are associated with keys. Alright, let's delve into the concept of hashing and hash functions. Imagine we have a special table where we want to arrange things in a smart way. We know that each thing comes with a unique code, like a secret symbol that only that thing knows. And we also have important stuff linked with each of these codes. So, when we want to store something in our table, we use this unique code as a guide. It's like a treasure map that tells us exactly where to put our items. We call this process as hashing. Now, let's say we have a key, which is like the code for a certain thing, and we have a special function called a hash function. Think of this hash function like a magical tool that takes the key as input and produces a new number. This new number tells us exactly where in the table to store our item. In other words, if we have a key called k and we apply the hash function h of x to it, the result h of x is like the address where we will keep the item linked with that key. It's like the hash function is guiding us to the perfect spot in our special table. So, hashing is the clever way of using keys and a hash function to quickly find the right place to store our stuff in our organized table. Okay, let's talk about something important when it comes to hashing. Hash collisions. Imagine you have this amazing guide that tells you where to put things in your special table. But sometimes two things might have the same guide that leads them to the same spot in the table. This situation where different things end up in the same place is called a hash collision. Now, when we have a hash collision, we are faced with a bit of a puzzle. We need to decide what to do with these things that want to share the same spot. We have a couple of tricks up our sleeves to solve this problem. One way is to use chaining. Think of it like a chain of connected boxes. When things collide, we create a chain of these boxes at the spot in the table. Each box holds one of the things that want to be in that same place. So, when we need to find something, we follow the chain until we get to the right box. Another approach is called open addressing. This is like a game of musical chairs. When something collides, we keep looking for the next available spot until we find one. It's like moving to the next chair if your favorite one is taken by someone else. There are different ways to do this, like linear probing, quadratic probing, and even double hashing. Alright, let's dive into the first way to tackle hash collisions, which is like giving each of our colliding items a cozy little corner. Imagine our hash function accidentally points two items to the same spot in our table. Now, instead of making them fight for that spot, we are going to make a small list right there. Think of it as a sort of shared space for these items. We call this method as chaining. Each spot in our table becomes like a tiny apartment complex. If more than one thing wants to move in, we just put them in a list, sort of like stacking up boxes. Now, each box holds one of our items and it also knows where the next box is. It's like a chain of boxes. So, when we need to find something, we just follow this chain of boxes. If we know which box we are looking for, we can quickly find it in its little stack. This makes things super efficient, even if a few items ended up in the same spot. Here is the secret code we can use to do this. When we want to find something, we just look in the box at the front of the stack. If we want to add something new, we just put it in the front of the stack. If we want to remove something, we just empty the box at the front of the stack. This chaining technique makes sure that our items always find a comfy home, even if they have to share a space sometimes. Alright, let's switch gears and explore another approach to tackle these hash collisions. So, this one is a bit different from chaining and involves a bit of a finders keepers attitude. Imagine we have our hash table, but this time if our hash function says a spot is taken, we are not going to put the new item there. Instead, we will keep looking for the next available spot until we find an empty one. So, if one spot is occupied, we start moving forward, checking each slot until we find an empty one. This way, we are still sticking to our table, just moving along it until we find a free space. That's why they call it open addressing. Think of it like looking for a parking spot in a crowded parking lot. You drive along, checking each spot until you find an empty one where you can park your car. Now, there are a couple of ways to do this open addressing. You can simply keep moving forward and filling up the next empty spot you find. Or you can follow a certain pattern to decide where to check next, like moving one step, or two steps, or more steps. So, to sum it up, open addressing is like trying to find an empty spot in a busy lot. You keep going until you find one. And in our case, when we need to find something, we use the same method to locate it. Different techniques used in open addressing are linear probing, quadratic probing, and double hashing. Let's dive into the approach called linear probing. It's a bit like trying to find a parking spot again, but this time with a slightly different strategy. Imagine our hash table is like a row of parking spots. When we want to park a car, or in this case an item, we calculate its hash and try to put it in a spot. But, oh no, someone else's car is already in that spot. So, what do we do now? Well, in linear probing, we just move to the next spot and try again. The formula tells us exactly where to check next. Here, I is a counter that starts from 0 and goes up by 1 each time we need to move to a new spot. H dash of k represents another hash function we use to calculate a new index. So, if the spot we calculated first is taken, which is h of k0, we move to the next one, which is h of k1, and then the next one after that, which is h of k2, and so on. We keep going in this straight line pattern until we find an empty spot. But here is the catch. Linear probing can sometimes cause a bunch of cars or items to be parked next to each other. Imagine if you had a row of cars in a parking lot that everyone tried to park in the first empty spot they found. That would create a big line of cars, right? That's the cluster problem with linear probing. it can make a bunch of items sit next to each other, making it a bit slower to find an empty spot later. So, while linear probing is quick to search and insert in many cases, it can sometimes lead to these clusters, which can slow things down a bit. Alright, let's explore another strategy called quadratic probing. Imagine we are trying to find a parking spot again, but this time with a different trick up our sleeves. In quadratic probing, we still want to park our car or item in a certain spot in the parking lot, which is our hash table, just like before. But instead of moving to the next spot right away, we are going to space things out a bit. Here is the formula we use to figure out where to check next. I know it looks complicated, but don't worry, I'll break it down for you. H dash of k is our trusty hash function. I is our counter, just like before, starting from 0 and increasing by 1 each time. C1 and C2 are positive numbers that helps us space things out differently compared to linear probing. So, let's say we are trying to park in a spot but it's already taken, which is h of k 0. Instead of moving directly to the next spot like we did in linear probing, we will space things out a bit. We will move to a spot that's c1 steps away, which is h of k1, and then if needed to a spot that's c2 steps away, which is h of k2, and then c2 squared steps away, which is h of k3, and so on. This spacing helps prevent those annoying clusters that can happen with linear probing. It's like saying, let's not all crowd in the same place. We give the parking lot a bit more room to breathe. So, quadratic probing is a bit like a more organized way of searching for a parking spot. We're still moving in a pattern, but we are not going to rush into the next available space. We are giving the parking lot some space to avoid those annoying traffic jams of parked items. Now, let's delve into another technique called double hashing. Imagine you are at the parking lot again, but this time you have not just one, but two clever strategies to find a parking spot. In double hashing, we are going to apply a bit of a tag team approach. When our primary hash function doesn't lead us to a free spot, we will call in the second hash function to help us out. So, here is the trick we will use. And don't worry, I'll break it down for you. h1 of k is our main hash function that gives us the initial spot. I is our trusty counter again, starting from 0 and increasing by 1 each time. h2 of k is our second hash function that kicks in when we need help in find a spot. So, let's say our primary hash function leads us to a spot but it's already occupied, which is h of k0. Instead of just moving to the next spot right away, we will call in our second hash function to guide us. The second hash function tells us how far to move from the initial spot, I times h2 of k steps away. And just like that, we have got a backup plan. If our primary strategy doesn't work, we use the second hash function to adjust our path. It's like having a buddy who guides you directions when you are a bit lost. So, double hashing is a bit like teamwork in finding a parking spot. Our first hash function does its best, and if things get tricky, our second hash function steps in to save the day. With this approach, we are more likely to finding a spot efficiently, even when the parking lot gets crowded. Now, let's talk about what makes a good hash function. Just like how some tools are better at solving specific problems, some hash functions are better at preventing collisions, those tricky situations when two pieces of data end up in the same parking spot. A good hash function might not be like a superhero that stops all collisions in their tracks, but it definitely knows how to make them happen less often. It's like having a magical sorting hat that tries its best to put students in their right houses at Hogwarts. Imagine you have a magical spell, your hash function, that you cast on each data item. This spell should scatter the items across the available sparking spots in such a way that they don't clump together too much. Just like throwing a handful of glitter into the air, you want the pieces to spread out and land in different spaces, right? So, even though a good hash function can't completely prevent collisions, it's skilled at reducing them. It's like having a recipe that makes sure your chocolate chips are evenly distributed in your cookie dough. In the world of hashing, a good hash function is a bit like a master chef who knows how to sprinkle just the right amount of seasoning to make the dish perfect. It might not make everything perfect, but it makes sure things a whole lot better. Here, we will look into different methods to find a good hash function. Alright, let's dive into the first method of hashing called the division method. This method uses a simple trick to find the parking spot for our data in the hash table. Imagine we have a key, let's call it K, and a hash table with M available spots. To find out where our data belongs, we use a special formula. Think of it like this. We are dividing the key K by the size of the hash table M, and the remainder tells us where the data should go. It's like sharing a pizza among friends. You divide the slices and see which one is left over. For example, if we have a hash table with 10 spots and the key K is 112, we calculate h of k, which equals to 2. So, the data with the key is 112 goes into the spot number 2 of our hash table. But there's a little twist. The size of the hash table M should not be a power of 2, like 2, 4, 8, and so on. This is because when we calculate k modulus m, we usually ends up with the lower bits of k, which might not be evenly distributed. So, if m is 22 and k is 17, our formula becomes h of k is equals to 17 modulus 22, which is also equals to 1, 0, 0, 0, 1 modulus 1, 0, 0. Resulting in a final value of 0, 1. So similarly, if m is 23, we get h of k is equals to 17 modulus 23, which is also equals to 1, 0, 0, 0, 1 modulus 1, 0, 0, resulting in a final value of 0, 0, 1. In cases where m is 2 to the power of p, like 2, 4, 8, and so on, the formula simply takes the lower p bits of k as the hash value. It's like picking out only a specific part of your phone number. So, the division method gives us a quick way to find a parking spot in our data in the hash table based on the remainder of the division. Just remember, for this method, avoid using hash table sizes that are powers of 2 to ensure a more even distribution of data. Alright, let's continue our journey through hashing by exploring the multiplication method. This method involves a bit of mathematical magic to find the right spot for our data in the hash table. The formula we use here is this. Now, what's all this about? Let's break it down step by step. First, we have our key k and a constant named a. This a can be any number between 0 and 1. But there's a special value that works pretty well, and it's about the square root of 5 minus 1 divided by 2. Just think of a as a seasoning that we will sprinkle on our key. Now, we want to find a slot in our hash table. we are going to do some math. K times A modulus 1. This might look a bit strange, but all it's doing is taking the fractional part of K times A. Just like when we divide a pizza slices in half and take the part that's left, that's the fractional part. Now comes the L-shaped symbols, which means we are taking the floor value. Imagine you have a floating point number like 3.8. The floor value is like the biggest whole number that's less than or equal to 3.8, and that's 3. So, putting it all together, the formula is saying take the fractional part of K times A, multiply it by M, which is the size of our hash table, and then round it down to the nearest whole number. This gives us the perfect spot for our data in the hash table. So why does this work? Well, it's a bit like doing a spin with a compass to find your way. The K times A modulus 1 helps spread the values out, and the floor operation ensures we get a nice whole index number. So that's the multiplication method, a bit of math and a sprinkle of a constant A to find the right place for our data in the hash table. It's like following a treasure map with a few clever twists. Alright, let's dive into universal hashing. It's a cool concept that involves a bit of randomness to make our hash functions even more versatile. So, imagine you're playing a game where you need to decide how to arrange your toys on a shelf. Universal hashing is like rolling a dice to figure out how to arrange them. You choose a hash function at random without even knowing what the keys or toys are. This randomness helps spreading things out and prevents any particular pattern from forming. Now, why would we want to do this? Well, think about it. If we always use the same hash function again and again, and our data happens to have a specific pattern also, we might end up with some slots getting crowded while others stay empty, right? So that's not very efficient. But with universal hashing, it's like changing the rules of the game every time you play. This way, our toys or keys are scattered around the shelf or hash table in a more unpredictable way. So, to sum it up, universal hashing is like addressing a sprinkle of randomness to our hash functions. It helps keep things balanced and fair, just like rolling a dice to decide where your toys go on the shelf. And that's how we keep our hash tables in great shape. Let's explore the various ways we use hash tables in the real world. Hash tables are like magical tools that helps us organize and find things super quickly. First off, imagine you have a huge library and you want to find a specific book without spending hours searching. Hash tables comes to the rescue. They are like librarian wizards that can instantly tell you where the book is located. This is why we use hash tables when we need to find things super fast, like looking up a word in a dictionary. Now, let's talk about secrets. Hash tables are like secret vaults. When you want to keep something secure, like your password or credit card information, hash tables help encrypt it. It's like turning your information into a secret code that only the right key can unlock it. So, in the world of computers, hash tables are used in cryptography to protect sensitive data. Lastly, think about organizing your stuff. Imagine you have a collection of stamps and you want to find a specific one without flipping through every page. Hash tables work wonders here too. They help us index and organize data efficiently, just like how you would use an index in the back of a book to find a chapter quickly. So, hash tables are like our personal organizer, fast finders, and secret keepers in the digital world. They help us find, secure, and sort data in the blink of an eye.